Welcome, Dr. Tausif. Dr. Tausif.
Hello.
Yes.
Yeah. Is it audible, ma'am?
Yes, it is audible. Dr. Tausif received his MTech in Computer Science and PhD in Parallel Computing from the Department of Computer Science and Engineering, Vishwasariya National Institute of Technology, VNIT, Nagpur, India in 2011 and 2017, respectively. Since July 2019, he has been associated with the Department of Computer Science and Engineering, IIIT Nagpur, as an assistant professor. His contributed journals. An Australian patent titled an IoT-based smart food cold chain transportation system is also granted to his account. He is NVIDIA certified DLI instructor for the Foundations of Deep Learning course. Welcome, Dr. Tausif, for the session. Thank you so much for accepting my invitation.
Thank you, ma'am.
Over to you. Yes, sir, it is
the screen
visible. Yes, sir,
Okay,
it is
fine.
visible.
Okay, good afternoon all. So today we are going to discuss this support vector machine and the kernel tricks. Okay, so this will be the content of the today's presentation. First of all, we are going to cover some preliminary definitions, like what is SVM and all, what do we mean by hyperplanes, then what is decision boundary. Okay, then after that we will see the intuition of the margin and the various notation that we will be using for defining the functional and geometric margin that we are going to cover next. After that, we will see the optimal margin classifier and the objective function of the same. Then we will see the demonstration of SVM using code, and then we will see the kernel intuition and why there is a necessity of the kernel along with the background of some kernel related information. Then after that we will going to cover this kernel tricks, and lastly we are going to just compare this logistic regression and SVM when we are going to use logistic regression, when we should use SVM and all. So this will be the today's content. Okay, before jumping to directly to SVM, just let me tell you in brief like the types of learning, where this SVM lies and what are the various other algorithms that comes under this category. So basically the learning is divided into three categories. Specifically, we can say four categories. If this semi-supervised learning is also considered as a separate category. So supervised learning, in which we are just given labeled data. Okay, unsupervised learning is there, in which only data is given without any labeling. Semi-supervised learning, we can say that it is just a combination or a mixture of supervised and unsupervised, wherein we can take one example in which some of the example are labeled and lots of example or lots of samples are unlabeled. And lastly, very important, is known as reinforcement learning, which is just based on the interactive environment between this agent and reward function. This logistic regression support vector machine comes under this category of this supervised learning, in which we are given data, and moreover the data is a labeled data set. Okay, so these are the general problems that can be solved using logistic regression, using support vector machine, classification and regression kind of problems. Now, yeah, as we have already discussed that it is a supervised machine learning algorithms. Basically, it is used in the discriminative hyperplane among these classes so that we can separate out the classes. So this is the overall idea behind this SVM. It is a discriminative classifier. Basically, two types of classifiers are there in machine learning. One is discriminative and another one is generative classifier. So if we look at this algorithm such as Neo-Bayes algorithm and the Gaussian discriminant analysis, they are known as generative classifier. And if you look at this SVM, logistic regression, these are the algorithms that come under this category of a discriminative classifier. The basic difference is that in discriminative classifier, we are just interested in categorizing the data set. Okay. Moreover, in generative algorithms, we are interested in identifying the pattern in the data. Okay. And after that, we categorize the data. So that is the generative difference between generative and discriminative classifier. Now just have a look of this support vector. Suppose if we take an example of binary classification, so this probably this belongs to one class and this uh, square or this square belongs to the another class. Okay, here also same example is there. Now just see, we are interested in dividing this or in categorizing this using a hyperplane. So just look at this. If we take this line, so possibly we need to draw two parallel lines parallel to this discriminator. Okay, so see this line is there which is touching to this sample, and see this dotted line which is touching to this sample. Okay, so the distance from this dotted line to the another dotted line is known as margin. Now just look at this. Here also we are discriminating this class with this class. Moreover, if we draw the parallel dotted lines to this solid line, just look at this line and this line. So here we can see the margin is large. Our intention is that in support vector machine, we need to separate or we need to classify these classes such that the margin is maximum. Okay. So as you look at this, this is one classifier, this is another classifier. It is characterized by this small margin and it is characterized by the large margin. So by looking at both of these classifier, we can conclude that this is the better classification as compared to the first one. Question is that how can we determine this line? Like what will be the slope of this line? So this is done using this SVM algorithm. So just support vectors. Support vectors are the data points. It is not this dotted line. These are the data points. Just look at this circle, this square. These are the data points nearest to the hyperplane. Okay, so see, this is the hyperplane, and in this class 1, this is the support vector, and in class 2, this is the support vector. Okay, these data points decide the position of the hyperplane, means the dividing hyperplane that we want to identify. So based on these data points or based on the support vector, the position of the hyperplane is finalized. Another thing is there, these points which are closer to this hyperplane can be considered as a critical elements of the data set. Just look at this point, this point. Basically, these are the points based on this hyperplane position is decided. So these data element or these samples are decided as a critical element of this classification algorithm. Okay, these also helps to build our SVM. One question is there, like the difference between generative and discriminative classifier. See, suppose if we take the plain Neo-Bayes algorithm, in which we are interested in identifying the pattern in the data. Okay. Moreover, after that, when we identify the pattern in the data set, then we go for the final classification. Okay. Like if you remember that formula, posterior is equal to likelihood multiplied by prior divided by that probability of A. Okay. So that is the plain Neo-Bayes formula, in which first of all we are interested in identifying probability of X given Y. So that kind of classifier are known as generative classifier. And which are the algorithm that comes under this category? Neo-Bayes algorithm, Gaussian discriminant analysis. These are the algorithm that comes under this category. Another category is purely discriminative algorithm. They are interested only in categorizing or classifying the data or the samples using any classifier. They are not at all interested in finding the pattern in the data set. The logistic regression support vector machine comes under this category of discriminative classifier. Is it clear? If any question is there at any point of time, just ask me. You can unmute yourself and then ask, or otherwise you can type in the chat box. Now see, what do we mean by hyperplane? Hyperplane is just a division. We take one example when this data is distributed in a two-dimensional plane. Okay, so this line is nothing but a separating hyperplane. If the data is distributed into three-dimensional space, just look at this: x-axis, y-axis, and z-axis. Okay, so here the hyperplane is nothing but this plane. If the data is distributed using one-dimensional, then single point is required for the separation. If the data is distributed in a two-dimensional, then line is required for division. If data is distributed using three-dimensional, then plane is required. So what is the generalization? Generalization is this: hyperplane in an n-dimensional space is nothing but n-1 dimensional subspace. Okay, just put put n is equal to 3 here. Just look at this example. Here n is equal to 3 means data is distributed in three-dimensional. So 3 minus 1 is a two-dimensional subspace. Two-dimensional subspace is nothing but a plane. Is it clear? Then after that we will see the margin and the intuition of margin. But before that, we will take one example of logistic regression. Then we will move to the once again our algorithm, that is SVM. Now just look at this. In logistic regression, what we will do, we simply perform this operation, theta transpose x. On this theta transpose x, we apply sigmoid function. Okay, the value or the formula of sigmoid is 1 upon 1 plus exponent of minus this entire expression, theta transpose x. Theta is a parameter vector and x is the input vector. Here we perform element wise multiplication, so we can consider as a dot product of two vector. Okay, after that you perform you apply sigmoid function. The range of sigmoid is in between 0 to 1. Just look at this. If this is the value of theta transpose x, okay, then the lower value is 0 and the upper value is 1. Based on that, we decide the threshold. Like suppose if the value of g of theta transpose x is greater than 0.5, then we consider this as a class 1. Okay. If g of theta transpose x is smaller than 0.5, then we consider this as a class 0. Which classifier we are talking about? We are talking about a binary classification in which labels are 0 and 1. Okay, remember labels are 0 and 1. We will change the notation in the next slide. Here the threshold is considered as 0.5. We can increase the threshold, we can decrease the threshold. Just look at this. This is h is nothing but my hypothesis. H of x is nothing but output of the hypothesis when applied on x. This parameter theta means h of x parameterized by theta. When it is greater than or equal to 0.5 or equivalently, then we can consider this as a class 1. We predict 1. Okay. And when we will get this h of x is greater than or equal to 0.5, when theta transpose x is greater than or equal to 0. Just look at this. When theta transpose x is greater than 0, then only this value is greater than or equal to 0.5. When theta transpose x is less than 0 or negative, then the value of this expression is nothing but less than 0.5 and we predict 0. This was all about the logistic regression. Now the confidence come into picture. What do we mean by confidence? Just consider that if the value of this expression g of theta transpose x is 0.9, somewhere around here, it means that we are very much confident that this sample x belongs to class 1. Okay. Moreover, if we see that g of theta transpose x is 0.1, very close to 0, okay, then we are very much confident then this sample x belongs to class 0. Is it clear? On the other hand, if the values are very close to 0.5, like suppose consider that g of theta transpose x is 0.52, very close to 0.5, okay, which class is this? It is considered as class 1. However, if we consider that g of theta transpose x is 0.48, 0.48 is very close to 0.5, but it is considered as class 0. In both of these circumstances, our confidence is very low. Why? Because why our confidence is very low? Because it is very much closer to the threshold. Is it clear? Okay, simply this is the part of this. If we predict 1, otherwise predict 0. Let's look at this one. Degree of confidence depend upon the magnitude of z that we already seen. Now just look at this picture. Come back to SVM once again. These are cross, means we can consider this as a class 1. These are the circle or dots. We consider this as a class 0. Now consider 3 points, point A, point B and point C. Suppose this is our separating hyperplane. Okay. Here point A is also considered as class 1, point B is also predicted as class 1 and point C also predicted as class 1. But we are very much confident about point A rather than point C. Why? Because it is closer to the hyperplane. So this was the overall intuition about this margin, and after that we will see the notation that we are going to use in SVM. See, previously in case of binary classification, we are using this label 0 and label 1. Okay, but instead of using label 0 and label 1 in SVM, we will use -1 for this label 0 and +1 for this 1. Is it fine? Only one difference is there. Instead of this label 0 or class 0, we are considering this as a label -1. So -1 means negative class and +1 means positive class. Specifically, you can consider in case of SVM binary classification. We are not talking about multi-class classification. We are simply talking about the SVM binary classification. Another thing, in the previous formula, we are using theta for parameter. We are using theta for the parameter, that the expression theta transpose x, and on top of that we are using non-linearity like g of theta transpose x. That g might be a sigmoid function, might be a 10h function. Okay. In SVM specifically, we are not using theta as a parameter. We are using w and b for representing the parameters. W is for weight and B is for bias. Now the hypothesis, we are just changing the previously the hypothesis is G of theta transpose X. Now what will be the hypothesis? Hypothesis is this: G of X, G of W transpose X plus bias. W transpose X plus bias. This is dot product of two vectors and the bias is added, and after that we apply this non-linearity. G may be a sigmoid function or maybe any other function, because here the values that we want is -1 and +1. Here see, previously this is h of x parameterized by theta in the previous slide. Here this is h of x hypothesis on this point x parameterized by w and b. So this is our new hypothesis. This is just a separate notation that we are using for SVM, Why we are using this separate notation, that we are going to discuss in a couple of time. The intuition is exactly same. Like g of z is predicted as 1 when z is considered to be positive. If z is negative, then it is predicted as -1. Okay, exactly same thing that we are doing in the previous slide. When z is considered as z is positive, then we were predicting +1, and if z is negative, then we were predicting 0. Okay, but instead of 0, which label we are using in this? We are using -1. So when z is negative, then we are predicting -1. Any point till this point? Any doubt till this point?
No, sir.
Now, two important concepts that we will discuss. The first one is functional margin and second one is geometric margin. Functional margin is nothing but a lowest relative confidence of all the classified points. Okay, means the classification is done correctly, that is accomplished with the help of functional margin. Now we will see what is this functional margin. Large functional margin represent a confident and a correct prediction. So what we want that classification should be correct. Moreover, we want that when we are saying that it is a correct prediction, then we should be very much confident. Okay, so two things are there, correct and confident, that we want from this SVM classification. The formula for functional margin for ith training example. Now consider that we are having 100 training examples. Okay, for each and every example, functional margin is separate. Okay, functional margin will be different for each and every data points. How we can going to define functional margin for the ith training example? Just look at this formula. It is represented using gamma cap for the ith training example. Formula is this, yi. What do we mean by yi? Yi is nothing but the label for the ith training example. W transpose xi plus b. Fine. If the value of I is equal to 1, if the value of I is equal to 1, then we will be computing this gamma cap for first sample, means functional margin for second sample. If the value of I is equal to 2, then we will be computing this gamma cap for the second sample and so on. Fine. See, there are two possibilities as we are dealing with binary classification. Either the label could be +1 or the label would be -1. Now, what will happen when the label is +1? Just look at this. When label is +1, then yi is nothing but +1. This is just a label. Okay. So W transpose X plus B, this should be greater than 0. This should be greater than 0. Then we consider this as a gamma cap of this particular sample. When the sample is belonging to the positive class, the entire expression is positive because +1 is multiplied to this positive quantity. Clear? When the label is -1, okay, so when the label is -1, then this yi is nothing but this -1. When this is -1, then this entire expression W transpose X plus B, this should be less than 0. When it is less than 0, then this expression is negative. When this negative expression is multiplied by this -1, then this entire expression is positive. Is it clear? When the label is +1, this expression W transpose X plus B should be positive. What is this W transpose X plus B? This is our Z in the previous slide. Okay. When Z is greater than 0, it is predicted as 1. When Z is less than 0, means it is negative, it is predicted as -1. Okay. Let me put one question, like how can you define when the classification is correct? How can you identify when the classification is correct? When this entire expression yi multiplied by this W transpose xi plus b, if it is greater than 0, can we say that the classification is correct? Or we can say that classification is correct for the class 1 category. When the prediction would be correct. See here, when the prediction would be correct, when this entire expression is nothing but positive, then only we can say that this prediction is correct, because when the label is +1, then we want that this expression is positive. Okay, so positive multiplied by positive is nothing but greater than 0. Okay, when yi is -1, means this label is -1, and definitely this expression W transpose X plus B should be less than Z, means this negative. So negative multiplied by negative is once again positive. So for all the samples like y cap for 1, y cap for 2, y cap for 3, irrespective of whether it is belonging to positive class or negative class, this expression should be positive. In that case only we will be considering this as a correct prediction. Contrary, if consider that this yi is positive, means label is positive, and this entire expression is negative, in that case what would happen? This positive multiplied by negative, so total expression is nothing but negative. And if it is negative, then we can consider this as a misclassification. Are you getting this classification? Correct classification and misclassification. One more thing that is very important with this functional margin is that, see here, formula for functional margin is this: gamma cap for the ith sample is yi multiplied by W transpose xi plus B. Just increase W. Instead of W, can you consider twice W? And instead of B, can you consider twice B? What will happen? See, if W transpose xi plus B is positive, then twice W transpose multiplied by xi plus twice B would also be positive. Fine. Instead of this W, we can consider 100 times W transpose multiplied by xi plus 100 times B. That is also positive. So what we can do, we can just increase this W or we can decrease this W. So we are having choice to increase or decrease this functional margin. Our ultimate aim was that we want to increase this confidence. So just look at this point. By exploiting our freedom to scale W and B, we can increase W, we can increase B. Okay, we can make the functional margin arbitrarily large. If you put 10W instead of W, and if you put 10B instead of B only, okay, then this functional margin would be large. Suppose previously you can consider that value of this entire expression is 10, and after putting W as 10W and B as 10W, B as 10B, the functional margin is nothing but 1000. Okay, now what we are doing? We are increasing the functional margin. So it won't affect on the classification. Instead, we are just increasing the functional margin. So we can make the functional margin arbitrarily large without really changing anything meaningful. So here, only point that you should note here, that we can increase W, we can increase B, it won't affect the classification. What we will achieve? We just achieve that confidence. See here, this was the functional margin in which we were discussing or we were targeting the correct classification. See here, this was the functional margin for ith sample. Now suppose if we want to define the functional margin for the entire training set, then what we should do? Functional margin for the entire training set is given by minimum of gamma I. Okay, so suppose 1 to n. What is n? N is the total number of samples or total number of example in our data set. Okay, so we just consider this gamma cap for first sample, gamma cap for second sample, gamma cap for third sample. We will take the minimum of all these values. That minimum value is considered to be the functional margin, gamma cap. Fine. This gamma cap of I corresponds to the functional margin for the ith sample. This gamma cap is nothing but functional margin for the entire training set. one more thing that I should clarify here. Here, functional margin can be increased or functional margin can be decreased. Now, suppose functional margin is increased, then we are not doing or we are not changing something in that particular classification model. Moreover, one more possibility is there. Instead of using W, we can use normalized W. Instead of using B, we can use normalized B. So what we can do? We can use normalized parameter. The benefit of using normalized parameter is that faster convergence of the model that we can achieve using SVM. So this was all about the functional margin. See, functional margin was definitely belonging to the correctness. Now geometric margin. Geometric margin is nothing but the calculating the actual distance. Now just look at this. This circle is there. Suppose consider this as a class -1 and this cross is there which can be considered as a class +1. These are just a label, +1 and -1. Now in geometric margin we calculate the actual value of distance. Just look at this. This is point A. Okay. What is the distance from this point A to the separating hyperplane? Okay. So this is just a perpendicular line to the separating hyperplane. We can consider the distance as AB. Okay, we will calculate this distance and that distance is nothing but the geometric margin for this point A. Previously, in functional margin, we are not calculating the actual distances. Okay, here in geometric margin, we will calculate the actual distances. Now see here. One thing is that this W should be orthogonal to the separating hyperplane. Just look at this. If this is the separating hyperplane, then this vector W, this is orthogonal. Why? Because anything or any point lies on this separating hyperplane, this should satisfy that W transpose X is equal to 0. W transpose X is equal to 0, or more specifically, W transpose X plus B is equal to 0. That's why we are saying that W is orthogonal to the separating hyperplane. Okay. Now, suppose we want to compute the distance, this AB. Okay. We know that this point A is there, but we don't know point B. For that, we need to identify what is the value of point B. And when we are having the value of point B, then only we will be in the position to compute the distance, this AB. Just look at this, how we can compute. W is a parameter vector. Okay. If this is a vector, if you divide this vector by its norm, okay, this is nothing but norm of W. If this vector is divided by its norm, it is nothing but a unit length vector. What is the relationship between this unit length vector and W? The direction of this unit length vector and this W is same. So W divided by this norm of W is just a unit length vector pointing in the same direction as of W. Okay. Just look at this. Now just identify this point P. What is point A? Point A is this xi. Okay. Just see here. Point A is this xi. I want to compute this point B. Okay. Now consider that or assume that the distance from A to B is gamma I. What is the difference between this geometric margin notation and the functional margin notation? In functional margin notation, we are using gamma cap, okay? And in geometric margin, we are simply using gamma. Just look at this gamma I. So this xi is a vector. Gamma I is just a scalar. So we cannot subtract a scalar from a vector. Fine. What we can do, we can just multiply a unit length vector by to this scalar. Then what will happen? This scalar is also get converted into a vector. What is the unit length vector in this direction? The same, W divided by W norm. Okay, this is the unit length vector. Now this is also vector and this is also vector. This entire expression, just look at this bracket. Xi minus gamma cap multiplied by W divided by norm of W. This expression is nothing but your point B. this expression is nothing but your point B, capital B. Just look at this. Now, any point lies on this hyperplane. Any point lies on this hyperplane satisfies that equation. Which equation? W transpose X plus B is equal to 0. Just look at this. W transpose X plus B. Which is that point we are talking about? We are talking about point B. And what is the value of this point B? Xi minus gamma cap, Xi minus gamma I multiplied by W divided by norm of W. Just look at this expression. Which distance we are interested in? Finally, we are interested in calculating this distance gamma I. Okay, just solve this equation and you should calculate, or you should be able to calculate this gamma I. How will you calculate? This W transpose is first multiplied by this Xi. Okay, then W transpose is multiplied by this W, so it becomes W square. Okay, see here, W is also vector and this is also vector. Okay, same vector is there, and if you take the square root of that multiplication, it is nothing but norm. Okay, now here W transpose W is there, so what we can write? Instead of W transpose multiplied by W, we can write norm of W multiplied by norm of W. Instead of W transpose multiplied by W, we can write norm of W multiplied by norm of W. So one norm of W is get cancelled out. Only one norm is remaining over here. So the expression is like this: W transpose X. Okay, this norm of W multiplied by gamma I. This is there with negative sign. This comes in the right hand side. Okay, and B is there. So the final expression for this gamma I is this: W transpose Xi plus B is there. Okay, gamma I multiplied by norm of W is coming in the right hand side, and that norm of W should come in the denominator. So you get this expression. Any doubt in the calculation of this expression? Now just look at this. Norm of W is displayed using this W transpose as well as using this B. Okay, so we are just distributing this norm of W over this first term and with the second term. So it will become W divided by norm of W transpose multiplied by Xi plus B divided by norm of W. This is nothing but the geometric margin for the ith sample. This is nothing but the geometric margin for the ith sample. What is the relationship between the functional margin for ith sample and geometric margin for ith sample? Functional margin for ith sample was gamma cap of I is equal to W transpose Xi plus B. Only this norm of W is there in denominator in both of these terms. Okay, so this is the relationship between functional margin and geometric margin. So geometric margin of WB, a training example would be this. Gamma I is just is equal to yi multiplied by this entire expression. Same thing is there if yi is nothing but the label. If this label is +1, then this entire expression should be positive. If the label is -1, then this entire expression should be negative. Why? Because this is just a distance. The distance may be in this side only or maybe in the other side. Distance should be positive. Same thing is there as it was happening in case of functional margin. So this is just a geometric margin corresponding to ith training sample. When functional margin and geometric margin would be same, what is the formula for functional margin? That gamma cap of I is equal to yi multiplied by W transpose X plus B. Okay, just assume that if norm of this W is equal to 1, if norm of W is equal to 1, in that case, this expression is what? Expression is this yi multiplied by W transpose Xi plus B. If norm of this W is 1, then functional margin and geometric margin is same. Another thing, geometric margin is invariant to rescaling of the parameter. Okay. However, the functional margin was not invariant to the rescaling of the parameter. In functional margin, we can increase the functional margin or we can decrease the functional margin. We can use normalized parameters also. But here, see, instead of W, if I can put 10W, okay, then what would happen? In denominator, norm of W is there. So it will just compensate that particular thing. And this rescaling is not possible over here. If you just write W as 10W and B as 10B, then also this gamma I, the value of this gamma I is not going to get changed. Okay, that's why we are saying that geometric margin is invariant to the rescaling of this parameter. This was the geometric margin for the ith training sample. Now we need to define the geometric margin for the entire training set. Is this minimum of all the training samples? Gamma I means geometric margin for the first sample, geometric margin for the second sample, geometric margin for the third sample. We will take the minimum one. That minimum quantity is considered to be the geometric margin for the entire training set. This was all about the geometric margin. Just take a quick review. In functional margin, we are targeting on the correctness. In geometric margin, we are targeting on the distance. Based on these two, functional margin and geometric margin, now we can define your optimal margin classifier for the SVM. This optimal margin classifier. What is our aim? Our aim is this. Yeah, before jumping to that objective function of SVM, what we want to separate out the positive and negative training example with a gap. We want that geometric margin should be maximum. Just look at this. And what is our assumption here? Our assumption is that the training set here is linearly separable. Means we can draw a separating hyperplane, like it's a line, it's a plane. Okay. So training samples are linearly separable. That is our assumption. It is also possible that training sample may not be separable. In that case, what we will going to do, that we will see when we will discuss the kernels and kernel tricks. Here we consider that it is linearly separable. Here we are interested in maximizing gamma. What is gamma? Gamma is the geometric margin corresponding to the entire training set. We want to maximize this gamma. What is gamma? Gamma is nothing but the minimum geometric margin. Okay, so we want to maximize this gamma such that this yi multiplied by this expression w transpose xi plus b. What is this expression? This expression is your functional margin. Functional margin for all the samples should be at least gamma. Okay, here why we are talking about functional margin? We should talk about the geometric margin because here we are looking at gamma only. But just look at this constant. Norm of w is equal to 1. When norm of w is equal to 1, then functional margin and geometric margin is same. Okay, that's why here we are maximizing this geometric margin, and this is our constant. Now problem is that this gamma may not be the convex function. This gamma may not be the convex function. So it will be very difficult to get the optimal value for this gamma. Now what we can do, and on the other hand, we do not want this constraint. Norm of w is equal to 1 because it is very difficult to identify such or to satisfy this constraint that norm of w is equal to 1. So our ultimate aim is that we want to remove this constraint from here. See the second alternative of this. Second alternative is this. Here we are maximizing once again gamma. See, this entire expression is nothing but gamma. How gamma and gamma cap is related? This gamma is a geometric margin and this is the functional margin. When this functional margin is divided by norm of w, then it is considered as geometric margin. Okay, so this expression is exactly the same. By writing this expression, we are just removing this norm of w from the constraint. One more change is there. See this condition. Here this is functional margin. This functional margin is greater than or equal to the geometric margin. But here what we are doing, this functional margin is greater than or equal to this functional margin. This expression is for the functional margin, and here also in right hand side we are using functional margin. We have removed that norm of W is equal to 1. One more problem is there with this. If we want to maximize this expression gamma cap divided by norm of W, it is exactly gamma. Okay. And I am saying that this is a non-convex function. If it is non-convex function, then definitely this is also non-convex function. Third approach or third alternative that we will do. If you remember that functional margin, we can arbitrarily make large this functional margin, we can reduce this functional margin. Can we make a constraint that functional margin is equal to 1? If we make this constraint as functional margin is equal to 1, then what we can do, we can just put gamma cap is equal to 1. Okay, just put here gamma cap is equal to 1. Then what this expression is? This expression is maximizing 1 by norm of W. See, maximizing 1 by norm of W is nothing but minimizing norm of W. I am repeating this. Maximizing 1 by norm of W is nothing but minimizing norm of W. Now see the final objective function. Here the constraint is this. Functional margin is set to 1. And this is the final objective function. Maximizing 1 by W is simply minimizing W. Okay. Such that this expression is there. Same expression we are writing over here is greater than or equal to gamma cap. Gamma cap is set to 1. This is the final objective function of any SVM. This is the final objective function of any SVM. Like parameters are there and those parameter vector is there that is represented with the help of vector W, and ultimate aim is that we want to reduce the norm of this W. So this was the optimal margin classifier. This was all about the case when we can separate out the data. Okay, when we can separate out the data. But it is also possible that data is non-separable. Just look at this. These circles are there and these squares are there. Can you put any line so that we can separate the positive and negative or class 1 or class -1? No, it is not possible. So this is nothing but the non-linearly separable data. These non-linearly separable data is handled with the help of kernel. Just look at this, what we can do over here. Method of using a linear classifier to solve this kind of non-linear problems. Okay, this is done using kernel function. What we will do, we will project this data to higher dimensional space. See, this is plane. Okay, what we can do, we can project this data into higher dimensional such as 3-dimensional, 4-dimensional space, so that we can separate out these two data with the help of a separating hyperplane or with the help of a linear classifier. And what SVM do? SVM uses the kernel tricks for transforming these data points. See here, these data points are characterized by 2-dimensional space. Kernel tricks use these transformation and it projects this for the higher dimensional space and creating the optimal decision boundary. How? See here. Suppose this is your X and this is your Y. Okay. I am putting one more dimension. The value of that dimension is x square plus y square. Okay. I am putting one more value. That value is fabricated based on x and y only. That value is fabricated based on x and y only. Suppose that expression is x square plus y square. Now just look at this. This is my third dimension. So x square plus y square, here the larger value is going up and this smaller value is coming closer to x-axis. Now we can divide this class 1 and class -1 using separating hyperplane. Now these are linearly separable. Ultimately what we are doing, we are converting this 2-dimensional data into a 3-dimensional space. These are the kernel functions that take lower dimensional input space and transform it into better dimensional space. But this is not comes freely. some time complexity of the function or kernel function is getting increased, but we can also compensate that increased time complexity that we will see. There are various types of kernels are there, such as linear kernels are there. If you are not using any kernel, then that can be considered as a linear kernel. We can use polynomial kernel, we can use Gaussian kernel, radial basis function kernel, RBF kernel is very important, mostly used. These are the various kernels that we can use. Now, just try to understand the mathematics behind these kernel tricks. Just look at this. Suppose this is our dependent variable and this is our independent variable. Single variable is there. I just want to predict my house price from this area of the house. Okay, so what if I directly write a line, then suppose the equation is y is equal to mx plus c. When it would be possible? It would be possible when the data is linearly separable. Now suppose data is not linearly separable, means y is not a linear function in terms of x. Then what you will do? If the price y can be more accurately represented as a non-linear function of x, what do we mean by this? Means some a multiplied by x cube plus b multiplied by x square plus c multiplied by x plus d. This is nothing but the non-linear representation in terms of variable x. Then what you can do, how you can achieve this using kernel tricks. See this is the expression y is equal to theta 3 multiplied by x3 theta 2 multiplied by x square. Previously it was simply x. Okay, now here x cube is one more variable, x square is another variable, x is one more variable. See here, we are not only expanding y, we are also increasing the parameters. How? Previously it was simply theta multiplied by x. Previously it was simply theta multiplied by x. This time here, 4 parameters are there. Theta 3 is also there, theta 2, theta 1 and theta 0. In any model convergence, what we do, we are ultimately interested in identifying the optimum value of each and every parameter. So see here, previously it was simply single parameter theta. Here we are 4 parameter. We are having 4 parameter and we need to identify the optimal value of each and every these 4 parameters. Now, this is R1, means only single variable was there. It is just transformed to 4-dimensional vector. 4-dimensional vector. So this transformation is represented using this feature map phi. This transformation is represented using feature map phi. It is a very simple example in which single dimensional value is getting transformed to 4-dimensional vector. It is also possible that this single dimensional value is getting transformed into 400-dimensional space, like x square multiplied by x2, x square multiplied by x3, like this. Okay, so this may be any possible value. Generally, we can say that this RD is getting transformed to RP, means d-dimensional vector is getting transformed to p-dimensional vector, wherein p is greater than d. Wherein p is greater than d. If we consider this for this example, then here the value of p is 4 and the value of d is 1. In this example, the value of d is 1 and the value of p is 4. Now, two things that we need to understand. This x was considered as attribute. It was given with the problem. This is our attribute. Okay. Now, from this x, we calculated x cube. From this x, we calculated x square. From this x, this is x. Okay, and this is x to the power 0. We can also calculate square root of x, okay, cube root of x. That is also possible. All these are nothing but features. All these are nothing but features. This attribute to feature is transformed with the help of this feature mapping phi. How we can represent this? Just look at this. Previously, it is just theta transpose x. This time it is theta 3 multiplied by x3, like this, and theta transpose phi of x. Only one difference. difference is there. Previously, it was theta transpose x, where theta one time, and here four values. Theta 3, theta 2, theta 0. Okay, this is theta 3, theta power 3. This is cubic function. Cubic function of which variable? This independent variable x can be viewed as a linear function over the variable phi of x. Is it possible? Yes, if we can represent this with the help of a vector. Which vector? This vector. Phi of x is equal to 1 x, x square and x cube. Okay, so this cubic function is viewed as a linear function over the variable phi of x. Here we are not considering this as cube of x. We are not considering it square of x. We are simply consider that this is a separate feature. This is one separate feature. This is one separate feature. Okay. We are not at all interested what is the power of this, how it is related to the attributes and all. Okay. So this is the idea. Now the problem is in terms of complexity, in terms of storage, in terms of complexity. Time complexity means previously only one multiplication was taking place. This time one multiplication plus two multiplication plus three multiplication plus four. Generally, we can say that previously it was computed with the help of order of d times. This time the computation is taking place in the in order of p times. Okay, what is d and what is p? Just look at this formula, this expression. Here d is 1 and p is 4. See one more example. Okay, before this example, just look at this. The depth of the kernel and the meaning of this. Suppose this is the kernel that we are interested to define, kz. In every backpropagation algorithm or in every model convergence, we need to multiply the two feature vector or two attribute vector. Okay. Previously, this was simply x transpose multiplied by z. Now we are considering that this is x transpose multiplied by z whole square. For this, we need to identify the valid feature map. If we can identify one valid feature map for this particular kernel, then only we can say that this kernel is a valid kernel, otherwise not. Now see, it is represented like this. K of xz, the left hand side is exactly same. It is equivalent to phi of x, comma phi of z. It is represented like this. We will see with the help of example. Don't worry about this. Now see the corresponding feature map. Assume that previously three attributes are there. Which three attributes? x1, x2 and x3. Previously three attributes are there, x1, x2, x3. Now we are not the demand of the problem is not compensated, is not covered with the help of these three attributes. Then what we will do means that they are not linearly separable. Then we will go to the higher dimensional space. So this is our feature map. We consider this x1 multiplied by x1, x1 multiplied by x2, x1 multiplied by x3, x2 multiplied by x1, and so on. So previously three attributes are there. Now this is our feature map. Can you tell me the value of d and p over here? Can you tell me the value of d and p in this example? See here, three attributes are there. So these 9 values are there. Okay, so the value of p is 9. In the previous one, rd is getting transformed with the help of feature map 5. The value of d is 3 and the value of p is 9. Just look at this. k of xz. This is exactly same. Here also k of xz is there. Now this k of xz is nothing but x transpose multiplied by z. X is one sample, z is one sample. Three attributes are there. So in sample x or in sample x, three attributes are there: x1, x2, x3. Just assume that this is this. X is equal to 1, 2, and 3. Okay, means the value of x1 is 1, the value of x2 is 2, the value of x3 is 3. One more sample is there, another example. The sample is z. Here it is represented as y. Don't worry about this notation. So here, suppose this consider this as z. So this is your z1, z2, and z3. Okay, 4, 5, and 6 respectively. Now here, our aim is that convert this attribute to the feature map with the help of phi. So convert this first vector a1, 2, 3 with the help of this feature map. What is this feature map? X1 is multiplied by x1. So here 1 is multiplied by 1. Then x1 is multiplied by x2. Then 1 is multiplied by 2. Okay. Then 2 is there. X1 is multiplied by x3. Then 1 is multiplied by 3. 3 comes here. After that, x2 is multiplied by x1, x2, and x3. Means 2 is multiplied by 1, 2, and 3. So it is 2, 4, and 6. See here, 2, 4, and 6 coming over here. After that, x3 is multiplied by x1, x2, x3. So this 3 is multiplied by 1, 2, and 3 respectively. Then you get this 3, 6, and 9. What is happening over here? This x is getting transformed by phi of x. This is x. 3 attributes are there. This is phi of x. 9 features are there. Attributes is getting transformed to this feature. Okay. Here, if we worked on attribute, then the time complexity is order of d. If we compute, or if the computation is happening on this, then the time complexity is order of p. Similarly, this was for the first sample. Compute for the feature map for the second sample. This is our second sample. Once again, we calculate this phi of y. Okay, just see here. 4 multiplied by 4, then 5, then 6. 16, 20, 24. Then once again, 5 is getting multiplied by 4, 5, and 6. Then you get this 20, 25, and 30. After that, 6 is getting multiplied by 4, 5, and 6. Then it is 24, 30, and 60. 36. Fine. After that, see, this phi of x is getting multiplied by phi of z. Okay. So this is a vector and it is also a vector. You perform element wise multiplication. 1 is getting multiplied by 16, 2 is getting multiplied by 20, 3 is getting multiplied by 20, and so on. And finally, you get the sum of all these. So this is 1024. 1024. Is it clear? Kernel trick is there. It is not at all required. It is not required to transform x into phi of x. It is not required to transform y into phi of y and then perform element-wise multiplication. All these things are not at all required. What our kernel tricks say that we know that k of xz is equal to x transpose x, x transpose z. Okay. Now what we can do? We simply perform these multiplication. This vector is get multiplied by this vector, means 1 is multiplied by 4, 2 is multiplied by 5, 3 is multiplied by 6. Just sum all these things and take the square of this. It is exactly 1024. It is exactly 1024. This k of xy is nothing but this expression, 4 plus 10 plus 18 whole square, 32 square is nothing but 1024. This is known as kernel tricks. What is the time complexity of this calculation? The time complexity of this calculation is order of p. This f of x calculation is order of p, f of y calculation is order of p. This calculation is once again order of p. Just look at this calculation. This calculation is order of d. What is the relationship between d and p? P is very, very large as compared to d. We want that computation should take place in order of d time only. So we do not require that this vector should get transformed to this feature vector. This vector should get transformed to the feature vector and then perform multiplication. Not at all required. This is a very simple example in which this three-dimensional or three attributes are there, which is getting transformed to 9 features. It may not always, it may not be the case always. Just look at this previous example. See here. In this example, three attributes are there: x1, x2, x3. Consider this phi of x is nothing but the all monomial of this x1, x2, x3 such that the power of the entire expression is less than or equal to 3. Now just look at this. How many features are there? 1, x1, x2, x3, then x1 square, x2 square, x3 square, x1, x2 like this. These many features are there. How many attributes are there? By putting first example, you you calculate phi of z by considering the second example, then perform element wise multiplication and then get the final value. On the other hand, what kernel tricks say that don't convert your attribute vector to the feature vector. Just multiply those attribute vectors smartly and get your work done. Just look at this. What is happening over here? This can be rewritten as x is getting multiplied to z. We are not using this phi of x. X is getting multiplied by z and take the square. X is getting multiplied by z, take the cube. This essay so this was the kernel tricks. And lastly, one more function, one more algorithm is very popular here in this category, that is logistic regression. Just take a relative comparison between this logistic regression and FVM, when we should use logistic regression and all. So basically, this logistic regression is very prone to outlier. Okay, however, FVM is not. And logistic regression is vulnerable to overfitting, but in SVM, less chance of overfitting is there. Okay, then it works very well with the identified independent variable, but this is not the case with SVM. SVM works well with unstructured data, semi-structured data, such as text and images also. Preferably, logistic regression is used for classification only. Okay, means we apply sigmoid function in logistic regression, so it is basically used for classification. However, this is not the case with SVM. It can be used with classification or it can be used for regression also.
होनी 6-7 6 या 7 होगी उसकी डेट एक दिन पुरानी है कुछ नहीं होता दे दो
This logistic regression is a probabilistic classifier. However, SVM is known as deterministic classifier, because in logistic regression we compute the probability, but this is not the case with SVM. It is just a deterministic classifier. Logistic regression is based on the statistical approach, but this SVM follows the geometric interpretation of the data. We had already seen when we have studied this geometric margin and functional margin. Yeah, this is just maximizing the posterior class probability. However, this maximizes the margin. This logistic regression is based on maximizing the posterior class probability, but here we are interested in maximizing the margin in case of SVM. When we should use logistic regression, when we should use SVM. Just consider this: n is considered as a number of features and m is considered as number of training examples. Okay, n features and m training examples are there. So this is some of the thumb rules are there. Like suppose if n is large and m is small. Okay. If it is the case, then use logistic regression or SVM with the linear kernel. It is exactly performing almost similar performance that you will get using logistic regression or using SVM. SVM with linear kernel is simply SVM only. Another thing is that if n is small between this range and m is some intermediate value, then what you can do, you can just use SVM. Okay. You can use some other kernel such as Gaussian polynomial kernel. And if n is small, this is the same, n is small and m is large. Okay. Then what you can do, first you should add some manually more features with the help of some augmentation and all, because here the number of features are very less. Okay, then you can use logistic regression or SVM with a linear kernel. Yeah, it is basically advisable that we exactly don't know like which logistic regression or SVM will perform better. So first you can go with the logistic regression and see how it is performing, and then you can go with the SVM and try for the different kernels. We will quickly see the working of this module with the help of a code. Just look at this. This is one file in which we are interested in categorizing apple and oranges. Okay, so total how many samples are there over here? We will build the SVM for this. So total around 40 samples are there. Okay, and what we are given? So
Sir, voice is not audible, sir.
Yes, actually, some problem was there in the network. Is it visible now?
Yes, visible, sir. Visible, sir.
Yes, is it audible?
Yes, now it is audible, sir.
Yes, is it audible now?
Yes, sir, it is audible, sir.
Okay, okay. Is the screen visible?
Screen is visible, sir. Visible.
Okay, okay. So just take a quick demo of this SVM. Previously, we had also seen that two classes are there. This orange and apple that we want to classify with the help of SVM. So we just import some libraries. Just see here importing pandas, then sklearn.svm. Here we are using this SVC, which stands for support vector classifier. After that, we are using After that, we need to provide that Excel sheet here. So how can we provide? Using this Google.colab, we import files and we just upload this. Just look at this now. So are you getting this choose file? So from this, I can provide that file here. Okay. So that apple.oranges.csv is provided over here. Then we can just read this using Panda. So see here. Now that Excel sheet is read. After that, see, training and test set is divided. So see here, test set is 0.2, means 20% of the data is used as a test set. So total 40 samples are there. So 20% is used as a test set. So total 8 images or total 8 samples can be considered as a test set over here. Now just look at this. After that, we are using this classifier. SVC support vector classifier is there. Which kernel I am using here? We have seen that various types of kernels are there, such as linear kernel, polynomial kernel, radial basis function kernels. Okay, so here RBF kernel that we are using. Okay, and then classifier.fit is nothing but the actual model training that we start over here. So see, this kernel is used and the model is trained. Now the model is predicted on the test data. So see here, classifier.predictx.test. Now we need to plot this confusion matrix. See here, this confusion matrix is plotted over here. So confusion matrix with the help of test data. So Y test means label of test data and this Y prediction. Okay, so both of these are provided over here. This is the confusion matrix. Total how many entries are there over here? This print CM. So 3, 4, 1 and 3, 0, 1 and 4. So total 8 values are there. And how many values are there in the test set? Total 8 values are there because 20% is data is used as a test data and 80% data is used as a training data. See, model accuracy that we are getting over here is 87.5. After that, we can just plot this what is happening in the back end with the training set and with the test set. So here, this is the visualization of the training data after model fitting, and once again we will plot this, visualize the prediction with the help of this matplotlib and all. So just run this cell. Okay, finally it is not coherent with the previous slide. Fine. So we just see this up till this point is fine. So model accuracy is just printed over here. We can test one more thing, like instead of using RBF kernel, we can use linear kernel. After that, we just once again run this cell. Once again, I think it is not connected from my end. Okay, fine. So what you can do, you can just use different types of kernel such as linear kernel, radial basis function, or polynomial kernels. Then one more kernel, that is Gaussian kernel, is very important. So you can just tweak this with the help of various kernel. You can see or you can observe how it is performing with the test set and all. So I think you are having the intuition how you can build the SVM model. Is it clear? Okay, any doubt from this, from the lecture or from this demo? We had seen this SVM, then the functional margin, geometric margin, then optimal margin classifier. After that, we have seen the kernels and the kernel tricks and how we can use these kernel tricks to reduce the computation cost and all. If any doubt is there, then you can ask.
Any doubts? Any questions that you would like to ask?
Pooja ma'am,
Sir?
will you help in sending this program? Is it possible, ma'am? Can you help
Pardon?
in sending this program? Hello?
Pardon?
Can you help in sending this program? Is it possible? Okay. Is it okay to send the program for trying execution?
If it is not
to try
related to
the
his
execution?
research, then definitely he would send it. I would
Sure, ma'am,
ask the
sure.
speaker if it is not
Okay,
related to his research, he would share it.
Okay. Sure, ma'am. Sure, ma'am. Right.
Yes.
I can share this program, don't worry.
Okay. The speaker will share the program. And I would take it from him and I'll share it with all the participants. Thank you so much, Dr. Tausif, for the hands-on exercise, and it was really very useful for all the participants. Thank you for accepting the invitation and giving us such a beautiful talk. Thank you so much.
Ma'am, I have one question. Is it essential to set random state? Is it essential to set random state?
Hello.
Tausif sir, the question is it essential to say random state?
For which functional margin or geometric margin?
Program, sir, in the program.
Oh, in
It
the
has
program.
a random state equal to 0.
Yes, that is required over here.
Okay. Okay. So some they are using the random state equal to 42, but we can set on our own.
Yeah, we can just change it, but it is mandatory to define that.
Okay, sir. Okay. Thank you. So can
Thank
you
you, sir.
kindly share your mail ID?
Yes, I can.
In the chat
Yes,
box.
I'm writing in the chat box. I'm just.
Please fill the feedback form. The link has already been shared with you. It's shared on the WhatsApp group also. The link will remain the same for all the sessions. Please share your feedback and that will add your attendance also. Thank you once again, Tausif sir, for delivering such a nice talk. I'm closing this meeting now and we'll meet tomorrow at 9:30. Thank you all the participants. Thank you so much for joining.
Thank you, ma'am.
Thank you.